I'm going to describe you the ALMA project, which is one of the biggest global projects ever built on Earth. It is located in the second region, so not far here from Antofagasta, in the Llama de Chasnantor, so it's a high plateau which you see here, which is at 5,000 meters altitude, so it's the highest observatory also on Earth. To give you an idea, the summit you see here is the Licancabur, which is above 6,000 meters. And the plateau extends over many kilometers, over a very smooth plateau of about 5,000 meters altitude. So I'm going to try to explain you how it works, why it was built, why people spend so much time and energy to build such a complex project in such a remote location, and give you a status of the project. And then at the end, after explaining how it works, or trying to explain how it works, to provide you some examples of scientific discoveries which are made with this project. So ALMA is a very nice acronym. It's sold in Spanish, as you know, and it stands for the Atacama Large Millimeter Submillimeter Array. So ALMA is an ensemble of 66 antennas which all operate together and observe a celestial source together. It's like a gigantic telescope. It's called an interferometer, and it observes in the wavelength range, which covers the millimeter and submillimeter region. I will explain that further along my talk. It's located at 5,000 meter altitude, and the antennas are not fixed. You can move them, and I will explain to you how you move them. You can have a configuration which is to your left here, which is called the compact configuration, where all the antennas are closely packed to each other, and then you can extend them over the plateau of Chasnantor up to 16 kilometers. The project is at 5,000 meters, and it's operated and has been built down into mountains at a location which is 2,000 meters below at 3,000 meters altitude. It has been built to operate for more than 30 years, and it started operating at the beginning of this year. The end of construction was last year. So, how is it working, and why are we doing this? The idea is to simulate a telescope of a diameter of 16 kilometers. As you know, the bigger the telescope is, the more sensitive you are, the more light you collect, and the more information you gather from the very weak sources which are scattered in the universe. Now, of course, engineers are geniuses, but nobody on Earth can build a telescope which is 16 kilometers in diameter. If you build that, it will just fall because of its own gravity. So the way you do that is to simulate a 16 kilometer or a 10 kilometer telescope by filling it in with smaller telescopes. So think about these little antennas, little being 12 meters in diameter, which are all scattered around a surface of about 16 kilometers. So you will think about it as pixels of your digital camera. So you have a plane which is only filled sparsely with a few antennas. So what you do in interferometry is that you use the rotation of the Earth to fill the whole diameter and the whole surface of your telescope. What is happening is when the Earth rotates, the source doesn't move, of course. It seems to move, but the Earth rotates. And while the Earth rotates, the relative location of each antenna changes with time. And in doing that, you fill in the aperture or the diameter or the surface of your virtual 16 kilometer telescope. So normally what you do is you wait until the source crosses around the sky. That's about 8 hours. But you can do it also quicker because there are so many antennas. So just remember that interferometry is a very clever usage of the fact that the Earth rotates on itself, on the axis, and that you use that to do imagery. That concept was done by Sir Martin Rayl and provided him with the Nobel Prize many years ago. So why is it so important to spend so much energy, time, and money in a project which observes in a millimeter and a submillimeter? I think that many of you don't even know that radio astronomers or astronomers were interested in that wavelength range. So we all know that when you look at the sky, you have eyes, and our eye is tuned to the visible. When you see the stars, you see the sun, and this is the visible which our eyes are tuned to. Why is our eyes tuned to this? You see the sun as a yellow object. Now the sun emits most of its energy in the yellow, and we are sensitive to the yellow because human beings sleep at night and work during the day, and so we have to be very attuned and very vigilant during the day. Hence, our eye is really sensitive and most sensitive where the sun emits its most energy. Of course, the sun emits over the whole wavelength range, and all celestial objects emit over the whole wavelength range from the X-rays down to the radio wavelengths. And here is a cartoon showing you the different wavelengths from radio up to the gamma rays. And the yellow here shows you the range of millimeter, submillimeter. So those are wavelength ranges which are 1,000 times bigger than the ones emitted in the visible, and are probing things which are very, very different. To make a long story short, the visible essentially probes the universe, which is the hot universe, so the stars and everything which is adult in star formation. But the millimeter, submillimeter, as you see here at the bottom, probes the cold universe. You're sensitive to temperature which are very, very cold, like minus 260 degrees Celsius. And in those regions of space, and I will come back to that later, in those regions of space, the stars are formed. There are very obscure regions where you can not see in the visible, but with the wavelengths in the millimeter, submillimeter just pierce through these clouds. So, again, the hot universe is best observed in the optical, and this is another Paramount big telescope in the second region. It's nearby here in Antofagasta in Paraná. It's, for the time being, one of the best optical telescopes, and it will be superseded in a few years now by a telescope which will be built next to it, which will be the ELT, which is a, I think, 41-meter telescope in diameter. So if you look at the Milky Way at night, you see that there is a whole sort of range of very bright stars, but also in the middle of the Milky Way you have very many patches which are dark. It's not because there are no stars there, they're simply because there are clouds of gas and dust which are absorbing the light coming from behind, from the stars, and hence you have the impression that there is no star there. It is particularly in those clouds that the stars are formed, because there are very massive clouds of matter which is collapsing because of gravitational forces, and with time there is an accumulation of gas and dust in the middle, which then produces a star which shines and then comes out of the cloud, and then you can observe it in the visible. If you would look at the Milky Way with millimeter, submillimeter eyes, you would see a completely different picture, where you won't see any of the stars in the optical, but you will trace all of the dark clouds. So the other message here is that the millimeter, submillimeter is complementary in terms of what you learn from a galaxy or an object from what you learn in the optical. And you need both to really understand what is happening in the universe. So this is another example where to the right you have a very famous galaxy. It's M51 for its little name. And to the right it's in the optical. To the left you see an image which is a trace in the millimeter region, where you trace a molecule, and I will come back to that later. And if you look very carefully, you see that in the optical you see all these very dark patches, which are the clouds, which are traced in the millimeter. So this is a nice example of how complementary these things are. Now another way to see that is to look at another very famous galaxy, which is called Centaurus A. And I show here a panel of different images taken at different wavelengths, from wavelengths in the X-rays, which raise a very energetic plasma, the particles, to very cold, where you see the millimeter, submillimeter, the upper right with ALMA. You see that the image you have from one wavelength to the other is very, very different, and you always trace different physical processes, different chemical processes, and it's a combination of all these images which provides you with a full description of what such a very complex organism like a galaxy really is. Now, The other thing is that you not only produce images, but the techniques which are used in the millimeter set emitted by a cloud of dust and gas. And if you do that, you will see that you are able to decompose that spectrum and understand what the composition of those clouds are, in particular what the chemical composition is. I won't give here a lecture about chemistry, but as you know, all the molecules have a very distinct way of interacting with light. It is like a signature. If you have two, what is called emission lines, you could identify what the molecule is. And this is an example here where you have a spectrum where you see different emission lines, and all of them have been emitted by different molecules. Today in the interstellar medium, there are more than 160 molecules which have been identified, and about a third of them were unknown on Earth. One example of things which were found in the universe and were not known on Earth and play a big role today is helium, for instance. Helium was found in the 19th century when people looked at the spectrum of the sun, and then they found helium on Earth. That's one example which is a very famous one, but there are other ones as well. So what is ALMA going to do? ALMA is very sensitive. It provides you a means to not only look at the molecules, but also measure the dust emission. And it is so sensitive and so versatile that it can probe the universe from very, very far away. When the first galaxies were formed, about 1 billion years after the universe was formed. And then you can look at the formation of stars and how they form in dark clouds. You can also look at the formation of planets around young stars and how the matter around young stars is orbiting and forming planets, for instance, like the Earth, where there may be people like here listening to a conference explaining how the universe is made. And then at the end, also, you can probe the chemistry and understand the complexification of molecules which are very simple at the beginning and become more and more complex, forming things like ADN, which is a form of life, as you know very well. So let me now try to explain how we do it and why we go to such great extents of energy and time to build an observatory in such a remote place, a beautiful place, as the Llano del Chascantón near San Pedro de Atacama. This is a picture of the Llano del Chascantón before the observatory was built. There were many locations which were searched for building ALMA, and this was selected as being the most fantastic one, providing the best opportunity to place the antennas from compact to very far away. One of the major reasons to go at an altitude which is roughly half to space or so is that to measure the millimeter, centimeter wavelengths, one of the major blockage is the atmosphere. It's the water which is in our atmosphere. And you're very sensitive to that. And so if you go very high, the column of water, the quantity of water which is above you diminishes, and so you can access to wavelengths you could not access, for instance, from the seaside, like here in Antofagasta. So the idea is to go as high as possible. Space is very expensive and very difficult, and so Chile is much better, and also it's nicer to live than in space. This is a picture taken a few years back, where you see that the antennas have been built, and let me now show you a few images of how it looks like when it's seen from above. This is an image where you see the whole infrastructure and how the plateau has been built with roads and paths, and you see here 7 antennas. It's a picture which was taken about 4 years ago or so, and the whole infrastructure was ready to receive all the other antennas. This is a picture which was taken recently with a helicopter, with a drone helicopter just flying over the array, and it provides you a very nice image and a sense of the size of the antennas. As you can see, you see people, you see cars, you see a crane. You realize how big a 12-meter antenna really is. So there are 66 of them. You also see that it's snow, and I just said you before, you need a very dry place, but of course you're in the mountains, in the Andes, and sometimes there is snow, although it's a very dry snow. This is a picture which is taken about a couple of months ago where you see most of the antennas. Today there are 64 antennas on this site, and there's still 2 to come to this high site. You see that it's a very dramatic landscape. And finally, this is a picture which is taken by one of our technicians working in ALMA, Jaime Branda, which is a very nice picture at night, where you see the antennas, and you see the night sky with the large magellanic clouds and the south magellanic clouds in the bottom. Now, I show that picture because it's a night picture, and most of the people think that astronomers essentially work at night. Now, in radio astronomy, you can also work during the day, because you're not sensitive to the sun, you are sensitive to the light which is scattered in the atmosphere. And so, as radio astronomy, people work 24 hours a day, every year. So it's a very efficient observatory, contrary to optical telescopes who only can observe at night. So, as I told before, the observatory is at 5,000 meters, and all the operations are done below at 3,000 meters. It's very difficult to work at 5,000 meters, and I think people living here know that very well. And so all the control of the antennas, all the maintenance of the equipment which is behind the antennas, and I will comment on that later on, is done at 3,000 meters in this area, which, as you see, is a very dry area as well. What you see to the right of these pictures is a big hangar and different camps where the antennas were all built. So everything which is on the plateau was assembled and built at 3,000 meters in the desert of Atacama. So, as I said before, it's a global adventure with about 20 countries which are involved in this project, and 3 big regions. It's East Asia, North America and Canada, and Europe, and also, of course, Chile. And here you have all the flags. And the project was inaugurated last year. It was an official inauguration with the then president of Chile, Piñera, and lots of representatives of all the countries, ministers, ambassadors, and so on and so forth. But a few days before, it was also inaugurated by the local community of San Pedro, of Tocanao, Paine, and all these beautiful villages. And there was a Pachamama which was made, and it was blessed. And since the project was blessed, since then the project works and operates and observes. So, what is the status of the ALMA project today? The project has been finished construction last year, or officially. There are still a few things that has to be done. But essentially it is done, and the 66 antennas have been built and delivered to the project. Everything has been tested, most of it, all the equipment, all the software, and the infrastructure is complete. And there are still a few tests to be made, but I won't bother you with the details. And most importantly, the science has started, and I will show you examples in a few minutes. There are still things to be done. It's not a closed project. There are many things you can do, and adding also new receivers and improving the project. I remember you that this project was built for 30 years. So this is a slide which is a bit complicated, and I apologize for it. But the purpose of this slide is to show you that the project is indeed complicated and a very complex one. And it's all driven by 2 important things. It's to have the best possible sensitivity. So in other words, to be able to capture the very weak light which is emitted by the celestial objects, and then to do that with the most explicit, what is called angular resolution. And angular resolution is what allows you to see very fine details in the objects you are looking. And so again, ALMA is working like a zoom array, like your camera. When you put the antennas very far away, you have a very explicit angular resolution which allows you to observe the details, the fine details of a cosmological object. To give you an idea, with ALMA, with 16 kilometers baseline, it allows you to discern the details of a 10 peso coin, which is at about 6 kilometers. So to do that, you have also techniques which allows you to do this, which are behind the antennas, and which from the antennas go to things which are called the correlator, the computador, and I will explain that a bit later, but I don't want to enter into the details, but the technique behind this is a very... And ALMA is probably the most sophisticated high-altitude building ever built. There's one building which is slightly higher in Tibet, which is at 5,100 meters, so it beats ALMA by 100 meters, except it's a railway station. I think everybody will agree that a base station, technically speaking, is easier than ALMA. So let me concentrate on a few items that makes ALMA operate. First of all, the antennas. There are three builders of antennas for each executives. I mean, that was a political decision. So it's built in East Asia, in North America, and in Europe. And there are four types of antenna. I don't enter into the details here, but the two types are 12-meter antennas and then antennas of 7 meter. There are 66 of them, and all of them, although they were built differently, have exactly the same specifications. To give you one example of a specification, the surface is so well known that it's better known than the quarter of the width of a human hair. That's about 12 microns. And the antenna is 12-meter diameter. And the reason you do that is that to collect all these photons, the real goal is to never lose any type of information. And if you had an antenna with a surface which was less accurate than that, then you would lose information. So you don't want to do that. So the ALMA project is also a wonderful example of a global cooperation and a project. Everything was built, devised, thought of, developed in all the regions in the north of the hemisphere, in North America, in Europe, and Japan. And while all the elements were built, they were then brought by ship or by airplane to Chile and then assembled here in the desert in the second region. When there is a problem with one of these equipment, a serious one, then it's brought back to the northern hemisphere, either in North America, in Japan, or in Europe. It's fixed and then brought back in Chile. That's really a global endeavor. So on the way to the region, sometimes you have exotic encounters here, like vicuñas, and this is a piece of, it's an antenna which is brought to the site. Once on the site, and once these antennas have been assembled with the different pieces which was brought from different regions, you have to bring it from 3,000 meters to 5,000 meters. So that is another huge difficulty, and that was resolved by building two fantastic trucks, which are called Auto Honor. They are the only two examples in the world. There are trucks with 6 wheels, which are independently movable. It allows you to transport these 100 tons antennas along the road to 5,000 meters. And that's absolutely marvel of engineering to be able to do that. The antenna shouldn't move, it should also have the same position and so on and so forth. And these trucks move with a very slow velocity of about 3 kilometers per hour. When you walk, you go faster. So it took a long time to go there. There's an image of one antenna brought to the site, and it takes about a few hours to go to the site. And once you're at the site, then you bring it to the position where you want the antenna to be. Once the antenna is on the site and you want to change the configuration, so you want to put the antennas farther away from each other, you bring one of these trucks on the site, you pick up the antenna, and you bring it farther down the road or down the plateau where you wish the antenna to be. The idea is to change the antenna's position over the whole year from very compact to very far away and then back to compact in a cycle that lasts for 12 months. Behind the antennas, there is very high-tech technology, and there are the receivers which are able to receive these wavelengths, and there are as many receivers as there are wavelengths or windows you can observe, and the millimeter, sub-millimeter, parts of the frequency is still absorbed by the atmosphere. And those are examples of these receivers. There are 17 of these receivers, and there are 730 different cartridges of these receivers installed in the plateau. So all data is then put in this blue box. There is one blue box per antenna, and in the blue box you keep temperatures which is very, very low, like minus 270 degrees Celsius. And the reason for that is that you want to have a noise which is very, very low, so you keep it very cold so that you're not annoyed by emission which is coming from warm environments. Once the receiver has received that very rare and very feeble photon, you have to transmit it and to amplify it. And that is done with technology which I will not describe in detail, which is called the backends. And that brings you down to the computer, which will sort of put together all the information and correlate all the signals of the different antennas. To correlate the signal of all the antennas, you need a computer which is very powerful, and which is called a correlacionador in Spanish, and which is indeed the most powerful computer on Earth, except it does only one thing. And it corresponds about to 3 million individual computers you would have on a PC or so. So you have at 5,000 meters altitude in the same region the most powerful computer on Earth, but again, it does only one thing, and it does it very well. So this is how ALMA works, and the reason you do all this is that I think that science, and I read somewhere, or I heard yesterday that Leonardo da Vinci said that one of the nicest things you can do is to discover new things. And I think one of the motor of science is to be curious and to understand what is surrounding you. So the astronomers, of course, want to understand what is surrounding you in the universe, and I think in the last 50 years or so, major discoveries have been made, and now everybody here can explain to their kids the history of the universe. And that I think it's a real achievement. The millimeter centimeter provides you views of well-known objects, and this is the first example I will show you. It is the moon. It's the closest by object we have. And to the left, you have an optical picture, and to the right, you have a picture taken with ALMA in a high-frequency band. Here again, you see how complementary the millimeter and the centimeter is, because as you see, the moon has a dark side here, but it's barely seen in the 70 millimeter when you see the full moon. So I'm not a moon specialist, but I think it's an interesting image anyway, which provides you, I think, a spectacular new view of looking at the moon. You also see all the craters, by the way. Let me go now further away in the solar system, and I will bring you in a journey which will bring you from very close by the moon to very, very far away. So this is another solar object, which is a comet. It's a comet which came into the southern skies in November, which was called Comet Ison. As you know, the comets are big chunks of ice. It's very dirty ice around a central cliff which is made of rocks. What is interesting here is that those objects are coming from very far away in the solar system, where the material is pristine and is sampling material from which the planets were made. So it's original material, and comets provides you a means to study what the material really is. Now, comets are very beautiful, as you see. They have a nucleus and a big tail. And an astronomer once said, comets are as beautiful as cats. They have tails, but have one characteristic also with cats, is that they do exactly what they want to do. And this comet did exactly what it wants to do. So it was a very bright comet. When it came near the sun, we observed it with ALMA, and one of the ideas was to see what happened when it was grazing towards the sun. What happened is that when it went very close to the sun, it just disappeared. It just was evaporated. We could not observe anything. So we observed that comet just before it grazed close to the sun, and this is an example of what ALMA is able to do. It's probably less spectacular than the optical picture, but it's very important, because what you're looking at is a spectrum where you look at all the material which is in the comet. And here you have two molecules, HCN and HNC. Forget about the names, but what you should notice here is that both the distribution of these molecules are very different, one to the other. And the right molecule is a product of the solar radiation which impacts the nucleus of the comet and releases gas. It makes chemical reactions where it reorganizes the basic atoms in other molecules. Now let me go further down the road here and give you an example of what ALMA sees when it looks into a dark cloud. This is a picture of a dark cloud taken with the VLT next door, I would say, where you see that there's a patch which is very dark, and in the upper corner to the left, you see sort of activity, which is an activity which is typical of a young star, which is just born, and emits at very high energy, about 100 kilometers per second or so, or more than many hundreds of kilometers per second, gas in the interstellar medium in opposite directions. Now that is a picture taken in the optical, and the next picture shows you what ALMA has seen. And this is the picture seen by ALMA. You see that with ALMA, you see much more because you really probe into the dark cloud, and you have a full picture of the full physical mechanisms which are occurring in this young star. There's a lot of detail here, and also with ALMA, you don't only see the gas and the different components, but you can also measure the velocities to a very high degree of precision. And hence you have a dynamical understanding of how the gas is ejected and how it flows in these cavities, which you see delimited in this picture very well. So again, if you think back and forth, you see how nicely ALMA peers into the darkness of these clouds where the stars are born. And that's one of the major goals and drivers of why we build ALMA in such painful project and with so much effort. Let's look at it further. One of the most interesting subjects which came alive about 20 years ago now was the realization that around stars which are in the neighborhood, there's also lots of material which is circling around the stars, and which is the material which was not used to build the star, the remains of the original cloud which formed the star. So those are the debris of the cloud that made the star, and those debris are the ones from which planets are formed, and we are not an exception. The Earth is a result of a debris of the disk which formed the star, which is the Sun for us, and out of which form Jupiter, Uranus, Saturn, Mars, and the Earth, and at the end ourselves. As you know, we had the result, what is called, of the dust of stars. So this is an example of a star which is nearby, where you see material very well dealing, the stars in the center, and you see that the material is turning around the star in a rotation which is typical of a rotation seen as in the solar system. To the left, you have an image taken from space by the Hubble Space Telescope in the optical, and there what you see is light of the star which is scattered, which is diffused on the dust grains of the disk. To the right, you see an image of ALMA, where you probe directly the dust grains, the emission of the dust grains, and you see how thin the debris disk is. Now this particular object is very well known because it's known that there's a planet which is circling around that star. And the supposition is that it's so thin that because you have two planets which are sort of shepherding this very thin debris disk around the star. Other examples, and a very nice discovery of ALMA, those are two other examples of matter which is circling around the star. They are less detailed than this image because those stars are far away. And I'll show you these images because if you look carefully, what ALMA sees here is the greenish patch here, and to the left also green, is you see that the dust emissions is only in one part of the disk. So it's very asymmetrical. And what you measure with ALMA are very big grains. I mean, the grains have sizes. It goes from very micro-sized grains to grains which are about a centimeter or so, up to things like the Earth. And this is the first evidence that indeed there is a mechanism by which, when matter turns around the star, there is a segregation at some point where the biggest grains eat the smaller ones, and so you have a segregation whereby there is places on the disk where you begin to form planets. And so those images are the real first imprints of planet formation around disks around young stars. As you see here, the disk is very big because you see a little elliptical picture on the upper side here where Neptune is circling. Neptune is one of the outer planets in our solar system. Another recent example is another star which has a central star which is about twice as massive as our Sun and about 10 times as most luminous. Now, this image is an optical image, again, I think taken by the Hubble Space Telescope. Now, if you want to study that with optical devices, it's very difficult, and the reason for that is the star is so bright that it just makes you blind and you cannot see anything which is around the star. So the technique which is used in the optical is that you use something which blocks the central star, and then you look at everything which is emitted outside of that diaphragm. So that's an example of it. And of course, ALMA doesn't have that problem because it doesn't see the star, but only sees what is around the star. And so you see that there is emission here, which is again a diffusion on the dust grains in the debris disk, which is very well delineated with the star. Again, you see here on the upper side the location of where Neptune will be. So it's a very extended thing. And again, to come back to the comets, those parts of the outer, let's say, solar type disk is where the comets are coming from. So that's an image of ALMA. You see it's a perfectly well-aligned disk, very symmetrical, and this is done in the dust emission. Now, the big surprise came recently when people looked at it in a molecule, which is the monoxide, carbon monoxide. It's very abundant, but it's a terrible poison for us because it's the thing which is produced when you have, for instance, fire in your house and you smell this carbon monoxide and you can die for it. It's poisonous. Now, in carbon monoxide, it looks like this. So if you look at it quickly, you see that in carbon monoxide, it's completely asymmetrical. And the reason for that is, it's very interesting, is that what is supposed to happen is that the dust grains collide with each other. There are bodies which are colliding like comets, and in colliding, they release their ice and their gases, which last for about 100 years or so. So what you see here in this debris disk is an action of ongoing collisions of debris, of big grains and so on and so forth, which you can see then with ALMA producing these spots of gaseous emissions in certain places where these collisions just happen. Now, chemistry, this is one example where it was a discovery again in a young star. What is interesting, to come back to this image here, is, as I told you, comets bring you the information of, in a very great detail, of what the composition of the gases which form the sun. Now we can do that in other stars, and it's interesting to understand what the composition of this debris disk is and how it changes and makes these very complicated molecules. Now, this is an example of the discovery of a molecule which is a sugar-type molecule, and it is a very poisonous type of sugar. You shouldn't put that in your coffee, you will die instantly. But the sugar, which is discovered here, has a very important role to play in the pre-ADN, so the pre-biological molecules which form life, and that was discovered in one of these young stars around a debris disk. So I think ALMA will discover more and more of these important molecules and probably provide incredibly important constraints and information about how life comes to be in place around stars which are evolved and around which debris stars are rotating. Now, stars are born, they also die. And when they die, they produce some of the most spectacular fireworks in the sky. And this is one example which was observed with ALMA, where you see a star which is typical about a few solar masses, so it's a bit more massive than the star of a solar system. And when a star dies, it sort of gradually and very slowly, when it's not too massive, expels its outer shells in the interstellar medium. There it does it, as you see, in a very fantastic spiral structure. And the reason for that is that stars, like human bodies, don't like to be alone. And about 3/4 of the stars are double, so are living with somebody else, and they rotate around each other. And when you have a rotation like that, you have one star is dying and expels the matter, and expelling the matter, it makes like a spiral structure, which you then can see and trace with ALMA. Now, stars can be also very massive, and when stars are very massive, they don't die like that star, but they die in explosions which are very, very spectacular. And those events are rare, and particularly close by. And in the southern skies in 1987, in February, in a large magellanic cloud, such a very massive star exploded. It was seen, it was so bright that it's completely dominated the emission of the large magellanic cloud. It could be observed with the naked eye. What is interesting in those stars is that they produce all sorts of matter. It's a huge nuclear explosion. And they produce gas, they produce also dust. And this is an image of this supernova remnant done in ALMA, made with ALMA, where for the first time we could measure dust which was freshly formed through also the reactions into this explosion. And what is important here is that that dust wasn't seen about 6 or 7 years ago. So it is dust which has been formed in only 3 years. This is an artist's impression of this supernova element, where the center part is where the dust has been formed. Now let me go farther away in galaxies, and of course, I mean, ALMA is a wonderful machine to understand how galaxies are behaving and what is happening inside the center of galaxies, or how stars are formed, and how it all spirals around this black hole which is at the center of those galaxies. Now, galaxies are sometimes isolated, but also, since they're very massive, they attract each other, and sometimes they collide. Now, when galaxies collide, it's also another firework. I used to say that in the universe, it's a constant big firework. It's like a fairy all the time. It takes a long time, but there are lots of examples because the universe is so big. This is an example of two galaxies which collided a long time ago, where you see the two centers here. And when you collide two galaxies, you bring the matter very close by, it densifies, lots of things happen. But what happens in particular is that we increase the formation of stars to a very, very high degree. And there are examples of collisions of galaxies where they have found that there are as much as many hundreds of solar type stars which are formed per year, and sometimes about 3 suns per day. So here is a composition of, in blue, you see the Hubble Space Telescopes, it's an optical picture, and in red it's the ALMA data, where you probe once again the very dark patches where these stars are formed at a very, very high rate of many suns per day. Another example of what ALMA can do is to zoom in into a black hole. This is also a very nice picture of an optical galaxy. I mean, it's seen in the optical. It has a name, a phone number, which I forgot. And at the center of the galaxy, there is a very massive black hole, sort of about 1,000,000 times the mass of our sun. It's the densest, most massive object in the galaxy, and around which all the galaxy is rotating. Now, ALMA provided a view of the center of that galaxy, and what you see here, superimposed on the optical picture, again in red, is a very complicated structure, which is like a spiral structure. And because we have the information of the velocities, we know that that gas is spiraling downwards and is eaten up by the black hole. So what you see here is how the black hole is just eating the gas and material, which is spiraling into the black hole gradually. And that's how the black hole is fed. Finally, and that's my last slide, is that ALMA and the millimeter submillimeter is a wonderful tool to probe the very first ages of the universe. For many reasons I can't explain, I won't enter into the details, but this technique allows you quite easily to measure galaxies which were formed about 1 billion years ago, after 1 billion years after the Big Bang, after the formation of the universe. Now there's another wonderful physical phenomenon which was predicted by Einstein at the beginning of last century, in 1910. It's the effect of general relativity. But it took about 50 to 60 years to observe it. What is happening is called gravitational amplification. And what happens is when you have a very massive object in the line of sight, that object acts like a lens and amplifies everything which is emitted from behind. So that was a prediction, and it was first observed in the 70s, and then more and more observed. And what is happening, it's not only amplifies by factors of 10 or more, but also distorts the object which is amplified in the back of this big galaxy or clusters of galaxies. Now, ALMA has observed it, and if you look at the upper panel here, the red spots are the distortions of galaxies which are very far away, which were formed about between 1 and 2 billion years after the formation of the universe, in which ALMA can detect very well and also map. I think what I haven't said here is that most of the examples I've shown you were obtained with only a very small fraction of the number of antennas of which ALMA is made. Typically, the biggest number of antennas is 20 here, because they were done at the beginning of the project. And you can only imagine what ALMA will do with 60 antennas, or 66 antennas. To give you an idea how sensitive ALMA is already, each of these images were obtained after 10 minutes of integration. If you put 3 times more antennas, you will only need a couple of minutes to obtain the same image. So again, ALMA is a very sensitive instrument. It will do very high resolution images of objects nearby, like comets, planets, also the same material around debris stars or around the stars, nearby galaxies, our own galaxy, but also galaxies which are from the early universe. So I think that project is a wonderful project. It provides fantastic results. There are fantastic results to come. And as always, I think what we are really looking forward to, not what we expect, but rather the big surprises of the ALMA will give. And I think that will be many, many surprises happening in the second region in the years to come. So let me thank you to listen to my talk, and excuse me that I've spoken in English. Thanks also to everybody who has made the ALMA project possible. This image is a blurred image, but there is all the photographs of everybody who contributed to the ALMA project. And again, thank you very much for your attention.